Quadratic expressions is the topic which we are going to discuss for today's session. Now, quadratic expression. How are the quadratic expressions derived? They have been derived from various different types of polynomials which we have discussed in the previous sessions. So let's start with the introduction of how the quadratic expressions are defined in mathematics. So for example, I take a polynomial. The various types of polynomials, say I take the linear polynomial ax plus b. We all know that this is a linear polynomial in one variable x because I found only one variable x in the entire expression. So this is a linear expression or a linear polynomial in one variable x, which is the unknown in this expression, and a and b are the constants. So similarly, if I have ax squared plus bx plus c is called a quadratic expression. So we identify that whenever the power of x is raised by one additional unit, we get the different types of polynomials by different names. Similarly, when I raise this to power 3, power 1, power 2 and power 3, ax cubed bx squared plus cx plus d is with power 3, so it is called a cubic polynomial or a cubic expression, and so on. So until we just increase the power of x by one unit, we get different types of expressions, out of which this is called quadratic expression, and hence we are going to study the quadratic expression in brief about how the properties, what are the various properties included in quadratic expression. So let's see with the quadratic expression definition. So when I come with the definition of quadratic expression, an expression or a polynomial. So with the definition, a polynomial of the form ax squared plus bx plus c is called a quadratic expression where the condition is that a, b and c are constants. A, b, c are constants which are either real or complex. So this is the symbol for complex numbers and this is the symbol for real numbers, and the condition says that the constants a, b, c identified in the quadratic expression might be either real numbers or it may also be the complex numbers or the imaginary numbers. So under these conditions, and here this is called, note, this is called a quadratic expression in one variable, so where the variable is identified to be x. So in this case, the unknown or the variable is identified to be x. And the second most important note is that a should not be equal to 0. So in this definition, I don't have a equal to 0, because if I have, say for example, reason, let's take this as a reason to support my statement that a strictly should not be equal to 0. So let's go on the contradictory part where I take a equal to 0 and see what happens to the quadratic expression. So let a equal to 0. So when a equals to 0, I substitute the value of a equal to 0 in the quadratic expression ax squared plus bx plus c. So in this case, substituting a equal to 0 in ax squared plus bx plus c, which is the general quadratic expression, then I get 0 times x squared plus bx plus c, with a being equal to 0. Therefore, on further simplification, this gives me bx plus c with the first term vanishing with multiplication of 0. The whole of the first term gets vanished and I get bx plus c. So this makes me understand that when a is equal to 0, it cannot be a quadratic expression, but this reduces to a linear expression, which can be clearly seen through the power of x being 1, which we already discussed in case of the introduction part. So when we have a linear expression for a equal to 0, this restricts the definition of quadratic expression. A quadratic expression is a polynomial strictly with its variable power being equal to 2. The highest power in a quadratic expression is identified to be 2. The highest power in a linear expression is identified to be 1. The highest power in a cubic expression is identified to be 3. Hence, we cannot call this a quadratic expression because the highest power here is identified to be 1. Therefore, for a equal to 0, quadratic expression reduces to linear expression in any case of b and c, irrespective of the values of b and c. Therefore, for a equal to 0, quadratic expression reduces to linear form. Therefore, my final condition is that a should not be equal to 0, is what I support with the second point. My third note about the quadratic expressions is that when I take this, each of them split separately, then the first term, ax square, is called the quadratic term. When I take the second term, bx, this is called the linear term. Now, what makes us call this a quadratic term and a linear term is again going back to the introduction. We have already identified that if the power of x is 2, then that gives us the definition of a quadratic expression. If the power of x is 3, it gives me the cubic expression. If the power of x is 4, it gives me quartic expression. If the power of x is 5, then it gives me quintic expression, so which we're going to learn in the further future classes. So when I have the power of x is 2, I call this as quadratic term because strictly the power of x is 2. And I call this a linear term. The second term of the quadratic expression is called a linear term because simply the power of x is 1. And finally, the last term c doesn't have any x. It is independent of the variable x. Therefore, this term is called the constant term. So c would be the constant term. So each of the terms of a quadratic expression has its own names. Say for example, I have ax squared plus bx plus c. Ax squared is the quadratic term, bx is the linear term, c is the constant term. So when I take any example of 2x squared minus 3x plus 4, then I can easily identify the first term, which is the quadratic term of this given quadratic expression, is 2x squared, and the linear term of this quadratic expression is negative 3 times of x, and the constant term of the quadratic expression is 4. Has its own definition with each of its term as defined, taken with an example. So now that we have seen various properties in the quadratic expression, we have to finally conclude with writing the standard or the general form of quadratic expression, because the standard or general form helps us in solving many problems taking the standard form as the base. So let's see how the standard form or general form of quadratic expression is denoted with its extended properties. So for example, I take the expression ax squared plus bx plus c. Then this is clearly a quadratic expression provided we have a not equal to 0 as discussed in the previous session. Then this is called a quadratic expression in general form or standard form. And let's identify each of them. We call the coefficients, the constants a, b, c are called coefficients of quadratic expression. Coefficients of quadratic expression. So each of a, b, c are called the coefficients of quadratic expression, where a has its own definition where it is referred as coefficient of x squared. So this is clearly identified as the coefficient of x squared, and this is clearly identified as coefficient of x because I can clearly see this multiplied with x. I can see this clearly multiplied with x squared, and this c is called a constant term, as we all know that it is independent of x, so it doesn't affect the quadratic expression with variable x. And this is a constant. So when I identify a in a given quadratic expression, I identify the coefficient of x squared as a. Say for example, I take in a different order of a general quadratic expression. With its own example, I take minus 7 plus 5x minus 2x squared. I clearly identify this to be a quadratic expression. The first condition for accepting this to be a quadratic expression is that a should not be equal to 0. Then let's see what are the values of a, b, c in this. Now clearly I identify a to be coefficient of x squared, which is negative 2, because I identify coefficient of x squared out here. So this makes me understand that the expression need not be in order as given in the problem, but we arrange the given problem in order of x squared, x, and constant. So we take in this proper order, provided however the problem is jumbled up. So in this case, a is negative 2 and b is, as we know, the coefficient of x, so that would be clearly 5, and c is the constant term, which is negative 7. Now since this is clearly not equal to 0, therefore we can call this to be a quadratic expression. So that is how I define a, b, c and justify on a being equal to 0 or not equal to 0, and then finally decide on a quadratic expression. Say for example, I have 3x squared minus 2. This is a quadratic expression or not, is what we are going to justify through that given example. So clearly we identify a, b, and c, where I identify a to be coefficient of x squared, so a is 3, but I don't have the coefficient of x, so I take the term missing out here as 0, and the constant term is negative 2, because simply this can be written as 3x squared plus 0x negative 2, where this is a, this is b, and this is c. And this clearly is a quadratic expression because a is 3, which is not equal to 0. Therefore, this is a quadratic expression. Say for example, I take so let's see if this is a given quadratic expression. Now when I take this, I clearly identify that a is 0 because coefficient of x squared is 0 clearly out here, and my b is minus 5 and my c is 4. But finally I conclude that this is not a quadratic expression because the condition a is not equal to 0 is not satisfied in case of this example. Therefore, since a is equal to 0, it doesn't form a quadratic expression. The reason we have already discussed, this reduces to a linear form when simplified through the 0 value, which gives me negative 5x plus 4. And therefore I get a equal to 0 implies is not a quadratic expression. This cannot be a quadratic expression according to the definition of a, is how I conclude. So now that we have discussed about quadratic expressions, let's come with the learning outcome from quadratic expressions as discussed in the session. So when it comes to learning outcomes, I firstly identify that a quadratic expression is a polynomial in one variable x. I identify only one variable. That is the first learning outcome in case of quadratic expression. Secondly, I identify that it is a polynomial expression. So I identify the polynomial of degree 2 is what defines a quadratic expression. So the degree must be 2. The power of x highest is 2. Then thirdly, I identify that a should not be equal to 0. A should not be equal to 0. Therefore, the condition is that a is not equal to 0 is one thing. And fourth learning outcome is that all the constants must be either real or can be the complex or imaginary numbers. So these are the various possible outcomes which are defined through the quadratic expressions in its standard form with all the properties. Now, let's take the definition of quadratic equation. So what is a quadratic equation and how is it different from an expression? In mathematics, we differentiate between an expression and an equation with an equality sign. So let's see the definition of quadratic equation in most simple words. If I take the quadratic expression ax squared plus bx plus c with a not equal to 0, then that expression reduces to an equation if I just equate this to 0. So a quadratic expression reduces to a quadratic equation with the quadratic expression equated to 0, thus forming a quadratic equation. So this is what defines the quadratic equation in its own definition. So from now on, I call ax squared plus bx plus c equal to 0 as the quadratic equation. So for example, I take x squared plus x minus 1 equal to 0. This is a quadratic equation, but not an expression. The left hand side of this equation is called the quadratic expression, but the whole of the equation is called quadratic equation. So finally, I conclude from this definition that when I equate the expression to equal to 0, I get an equation. In this case, we define the quadratic expression defined with equal to 0 as quadratic equation. Now all the rest of the terms would be same, where the condition is that a should not be equal to 0 and a, b, c can be either real or complex. So the definition would be the same as that of quadratic expression, but the only additional definition being equal to 0 is how I define the quadratic equation. Now, when we have defined the quadratic equation, there are many properties which arise from the quadratic equation. Say for example, I take a linear equation in its more simple form as 2x minus 4 equal to 0. This is a linear equation, and when I want to find the value of x, I simply take 2x equal to negative 4 on the right as 4. Thus, this gives me x equal to 4 over 2, and thus on cancellation gives me x equal to 2. So what is this x equal to 2 related to its respective linear equation? We just identify x is equal to 2 is the solution of the given linear equation, or this is called the zero of the given linear equation. In similar grounds, a quadratic equation ax squared plus bx equal to 0 also has its own solutions for the values of x. And the next session is about how we can find the values of x, or how we can solve the given quadratic equation by using various different mathematical properties. Now, to find the roots or zeros or solutions of the given quadratic equation, so the solution of a quadratic equation has various names through which we call them either roots or zeros or solutions, means one and the same. So before we start with how to find the solution of quadratic equation, let's come with the basic introduction that if I have linear equation has only one solution, or it has only one value of x which can be identified through the linear equation. Now, when I increase the power of x to 2, ax squared plus bx plus c equal to 0, the quadratic equation which we call has two solutions, is how we identify. So when I increase the power to 3, then we have three solutions. then power n will have n solutions, is how the polynomial expressions or polynomial equations are defined. So similarly, when I have the cubic dx square, then the cubic equation, which we call this, has 3 solutions. Similarly, when I take the polynomial of degree n has let me take this as a1, a2 and an as the constant equal to 0 has n solutions. So this is how we define for polynomial functions or polynomial equations, where if the highest power is 2 for x, the variable x, I have 2 solutions. If the highest power is 3, I have 3 solutions. The highest power is n, I get n solutions. Therefore, a quadratic equation always has 2 solutions or 2 roots or 2 zeros. So coming to this, if I wanted to find the zeros of the quadratic expression ax square plus bx plus c equal to 0 with a not equal to 0, this has two solutions, or it can have which are distinct, 2 solutions which are distinct, or it can have the possibility that it has one repeated solution. So this is one more possibility of the quadratic expressions. So there are 2 different possibilities of having the roots or zeros or solutions of the given quadratic equation. Now let me take the quadratic equation this, then it is identified that there are 2 types of solutions for the quadratic equation. One being that there are 2 solutions which are distinct, not equal to each other. The other possibility being that there's only one solution which is repeated twice. So let's see the different cases through this. But before that, if I have, say, note, if alpha is the root of the quadratic equation ax square plus bx plus c equal to 0, then my root is defined as that value which, when substituted into the quadratic equation, gives me 0. So therefore, if alpha is the root of the quadratic equation, this implies when I substitute alpha in place of x, this should give me equal to 0. This is how the roots are defined. That implies when I substitute x equal to alpha, then I get a alpha square plus b alpha plus c is equal to 0. So whenever I have any root alpha for the given quadratic equation, it is indirectly implied with substitution leading to 0. Is how I define the roots in general sense. Say for example, if I have the quadratic equation 2x square minus 5x plus 6 equal to 0, then randomly let me substitute x equal to 3. Let me take this as x square minus 5x plus 6 equal to 0. So if I take the quadratic equation with coefficient of x square equal to 1, coefficient of x equal to -5, and the constant is 6, then if I substitute x equal to 3, let's see what happens. 3 square minus 5 times of 3 plus 6, which on simplification gives me 9 minus 15 plus 6, where 9 plus 6 is 15. 15 minus 15 on the whole for simplification gives me this value to be 0. So this makes me understand that when I substitute x equal to 3 in the quadratic equation, this reduces to 0. Therefore, 3 is said to be the root of the given quadratic equation. Now since x equal to 3 substituted gives me 0, therefore I can call x is equal to 3 is the root of x square Therefore, x is equal to 3 is said to be the root of the given quadratic equation x squared minus 5x plus 6 equal to 0. So this is how I identify the roots through substitution in the given quadratic equation. Equal to 0 is the root, not equal to 0 is not the root, is how I understand the concept. Now, how to find the roots is the biggest question which comes followed from the continued session. So how to find the roots of the quadratic equation in its general form or the standard form ax squared plus bx plus c equal to 0 with a not equal to 0. So how do I find the roots of this standard form of quadratic equation? So let's see through the derivation. Say let alpha be one of the root. Let alpha be. Now that this quadratic equation has two roots because the highest power is 2, so we need to identify two roots which can be possible through the given quadratic equation. So what I do is I'll take one of the root as alpha, then I would like to find what exactly would be alpha in its derived formula. So let alpha be the root of the given quadratic equation ax squared plus bx plus c equal to 0. So in this case, because alpha is the root of the quadratic equation, that alpha must satisfy the given quadratic equation when substituted in place of x. Therefore, x equal to alpha implies this quadratic equation reduces to a alpha squared plus b alpha plus c equal to 0 is how this equation reduces, because x equal to alpha is the root of the given quadratic equation. Now, I try to simplify this by taking a alpha squared. I would like to take a common out here so that I get alpha squared plus b by a of alpha plus c by a equal to 0. So I'm taking a common out of the entire equation, so that when I take a common out of alpha squared, it's only alpha squared remaining inside. But when I take a common out of it, then I have a in the denominator. Because I don't have a term, this is how I take common, so that when I multiply, the a gets cancelled and I retain back b alpha in its original form. Similarly, when I just want to have a taken out of c, it can be taken out by c by a times, is how I remove a out of the brackets. Now that implies alpha squared plus b by a alpha plus c by a is equal to 0 by a, which is 0. Now since a is not equal to 0, only then I can divide this on the right hand side. But if a is equal to 0, I cannot restrict in taking this. My restriction is that I cannot take a to the right and divide by, because denominator being 0 is not defined. Simply because if a equal to 0, then it gives me the form 0 by 0 when I go to the right, which is an indeterminate, or an undefined value. Therefore, I can take this to the right strictly because a is not equal to 0, and therefore I get this to be 0. Then finally my expression on the left hand side is alpha squared plus b by a alpha plus c by a equal to 0 is finally what is reduced from the previous equation. Now I would like to make this a perfect square or a complete square form. So therefore I just bring it in the form a squared plus 2ab plus b squared, which gives me a plus b whole squared concept. Therefore let's try to see how we can convert this into a square formula, a plus b whole square. So alpha squared 2 times of b by 2a into alpha plus c by a is equal to 0. Therefore a squared plus 2ab plus, adding and subtracting this, gives me the perfect square form, because I have a squared plus 2ab plus b squared is not available. So I add and subtract this so that this becomes a perfect square. a squared plus 2ab plus b squared, which is a plus b whole square. So therefore, this gives me a plus b whole square, and this would be minus b squared by 4a squared plus c by a equal to 0. And this, on further simplification, gives me alpha plus b by 2a whole square plus 4a squared being the LCM, and then gives me zero. The LCM of this and this gives me b squared minus 4ac by 4a squared equal to 0. Therefore, this, on further simplification, gives me alpha plus b by 2a whole square equals, this taken on the right gives me b squared minus 4ac by 4a squared, taken on the right hand side of the equation. Now this being a square, when I remove the square, it reduces to root on the right hand side, because when x squared is y, that implies x would be plus or minus root y, is how I understand the concept. Therefore, when x squared is y, x would be plus or minus root y. So x squared equal to y gives me x equals plus or minus root of b squared minus 4ac by 4a squared. So this is strictly using this formula out here, taken out here. Therefore, this would be further simplified, gives me alpha plus b by 2a is plus or minus root of b squared minus 4ac, but 4a squared under square root of 4 is 2, and root of a squared is a. Therefore, this reduces out of the root as 2a. Then my alpha is, I take this to the right so that I get minus b by 2a plus or minus root of b squared minus 4ac by 2a. So taking 2a common in the LCM, this reduces to alpha equal to, gives me alpha equal to minus b plus or minus root of b squared minus 4ac by 2a. This is how we derive for the root. So this is said to be the root of the given quadratic equation. So whenever I have a quadratic equation in general form with a not equal to 0, then the two roots which we identify for this would be one with plus minus b plus root of b squared minus 4ac by 2a is one root, and minus b minus root of b squared minus 4ac by 2a is the other root of the given quadratic equation. So continued from, we have that for the given quadratic equation ax squared plus bx plus c equal to 0 with a not equal to 0, I get two roots which are given by the formula by 2a. So there are two roots, one given by plus and the other given by minus. Therefore, when I take distinctly, one of the root is minus b plus root of b squared minus 4ac by 2a, and the other root is minus b minus root b squared minus 4ac by 2a. Usually these are the two roots which gives me the roots or the zeros of the given quadratic equation. So let's see with an example how we can find the roots using the formula. And this is said to be the formula for finding the roots of the given quadratic expression. Say I take an example. I wanted to find the roots or the zeros of the given quadratic equation x squared minus 5x plus 6 equal to 0. Now when I see the left hand side, the quadratic expression here is x squared minus 5x plus 6. Therefore, identifying a to be the coefficient of x squared, which is 1 times of x squared. Therefore, my coefficient of x squared, which is a, is 1. Then the coefficient of x, which is b, is negative 5, because I identify this to be a, b, and c. So b is minus 5 and the constant term, which is independent of x, is identified to be 6. So once we identify the values of a, b, and c, we substitute in the formula so that we get the roots of the given quadratic equation. So substituting in this formula, minus b plus or minus root of b square minus 4ac by 2a, I get this to be minus b plus or minus root of b squared minus 4ac by 2a is how I substitute and simplify. Now this, on further simplification, gives me negative times of negative 5, which is 5 plus or minus root of minus 5 whole square, which is 25, minus 24 by 2 times of 1, which is 2. This, on simplification, gives 5 plus or minus root 1 by 2, which is nothing but 5 plus or minus 1 by 2, because root 1 is 1. Therefore, I have two roots here. One is 5 plus 1 by 2 and 5 minus 1 by 2, which gives me 6 by 2, which is 3, and this further gives me 4 by 2, which is equal to 2. Therefore, I identify x equal to 2 and x equal to 3 are the roots of the given quadratic equation. So x equal to 2 and x equal to 3 are the roots for the given quadratic equation x squared minus 5x plus 6 equal to 0, is how I derive the roots using the formula, the basic formula. So now that we have discussed about the roots of quadratic equation, and we have always identified that there are two roots for the given any quadratic equation given. Now let's see how one repeated root can exist for a quadratic equation, as we have already discussed in the previous session. So let's see one specific example. X squared is equal to 0. So I have this quadratic equation where let's see how we can find the roots using the formula. So in this case, I identify a to be 1 and b to be negative 14 and c is 49 as taken in this form. This is a, this is b, and this is c. So let's substitute this in the formula and find the roots. So to find the roots, I have the formula x equal to minus b plus or minus root of b square minus 4ac by 2a, which on further simplification gives me minus b plus or minus root of b square minus 4ac by 2a, which on further simplification gives minus of minus is plus root of 14 square is 196, or by 2. So this gives me equal, so that when on cancellation gives me root 0 is 0. Therefore, I get this to be 14 plus or minus root 0 by 2, which on further simplification gives me 0 by 2. Therefore, I get two roots out here. So one given by 14 plus 0 by 2 and 14 minus 0 by 2, and thus this gives me 14 by 2, which is 7, and this gives 14 by 2, which is 7. So I get two roots out here, but I identify here that both the roots are same, which is called one repeated root. So this is the case where I have x is equal to 7, 7, where these two are repeated twice. Therefore, in this case of an example where you get repeated roots, the given quadratic equation x squared minus 14x plus 49 is said to have is the repeated root of x squared minus 14x plus 49 equal to 0, is how I understand the repeated root concept. So there are two types of roots. One is the two roots of quadratic equation might be distinct as seen in the previous example, but the two roots might be equal, called the repeated root of the given quadratic equation. So the roots can be equal or may not be equal. If equal, they are called repeated roots. If not equal, they are called distinct roots or zeros or solution of the given quadratic equation. Discriminant is the next definition what we're going to see in the properties of quadratic equations. This is an extended property. Let's see what a discriminant is. The expression b square minus 4ac is called the discriminant of the given quadratic equation, and it is generally denoted with delta. This is the notation for discriminant, where delta is b square minus 4ac is called the discriminant of the quadratic equation. Delta equal to b square minus 4ac is called the discriminant of the quadratic equation equal to 0. So this is how we identify the discriminant of the quadratic equation. This not equal to 0 with a not equal to 0 is how I identify the discriminant, and denoted with delta. This is read as delta. So let's take an example to find the discriminant of a quadratic equation. So when I take an example quadratic equation, 4x squared minus 3x plus 11 equal to 0, then minus 11 equal to 0, then I would like to find the discriminant of this quadratic equation. So before we find the discriminant, I identify the values of a, b and c from the given quadratic equation, where a is clearly the quotient of x squared, and this is b and this is c. So a is 4, b is minus 3 and c is minus 11 are the three constants identified from the given quadratic equation. Now we know that the discriminant denoted by delta is given by the formula b squared minus 4ac. Therefore, when I substitute b as negative 3 squared minus 4 times of a times of c, on further simplification gives me the value of delta. So that this gives me 9 minus of minus plus 4 4 16 176, and this gives me the value as 185. Therefore, the discriminant of this given quadratic equation is identified as delta equal to root 185. Root of this as 185, not the root. So delta is 185 for the given quadratic equation. So next, let's connect the discriminant with the roots, expressing the roots in delta form. Or discriminant form. So delta or discriminant form, we see how the given roots can be expressed in discriminant form. Say I have the quadratic equation ax squared plus bx plus c equal to 0 and a not equal to 0, then we all know that delta is b squared minus 4ac. So using this concept, let's see how the roots can be simplified, reduced to delta form. So we all know that the roots of the given quadratic equation in general form is given by the formula minus b plus or minus root of b squared minus 4ac by 2a. That implies my x with b squared minus 4ac being equal to delta can be replaced inside the root with delta, is how I convert the given roots into delta form. So this would be minus b plus or minus root of delta by 2a. So I substitute the value of delta inside the root and I get this in the roots in delta form. one root being with plus and one root being with minus is how I get the roots in delta form. So when we substitute the delta by simplifying, we get the answer directly for the root. Now next, what is the significance of delta? The discriminant. What is the use of delta? The purpose of inventing delta to be b square minus 4ac is very important in quadratic equation inventions. So significance of delta is clearly identified here because delta is clearly identified inside the root. So if delta is positive, the root is defined for a positive number. If delta is negative, then it is not defined for root of a negative number. It becomes complex. Therefore, delta decides the nature of the roots. So delta decides the nature of roots. So the nature of roots can be easily identified through its presence inside the root. So delta, firstly, I identify that if delta is greater than 0, that implies the root is defined for a value which is positive or greater than 0. That implies roots are real and distinct. Real and distinct. They cannot be imaginary numbers. And next, when delta is equal to 0, the whole of this term vanishes, and therefore the whole of plus or minus 0 gets vanished, and therefore I get only one root, which is a repeated root. As I can see clearly here, if delta is substituted with 0, then this becomes minus b plus or minus 0, then it reduces only to one unique term. That implies roots are real and equal. So in this case, I get two equal roots or one repeated root, which is nothing but x equal to minus b by 2a. I get the root to be minus b by 2a as the root when delta equal to 0. When delta is greater than 0, I get two roots which are real and distinct. When equal to 0, I get only one root which is repeated. Thirdly, when delta is less than 0, root of a negative number is not defined on real plane. Therefore, root of a negative number is strictly an imaginary or a complex number. Therefore, when delta is less than 0, I don't get real roots. I get roots are complex or imaginary. Now, when delta is less than 0, the roots are complex or imaginary. So these are the three cases which define the roots in being either real and distinct, or real and equal, or complex or imaginary, with strictly with the definition of discriminant greater than 0, equal to 0, and less than 0, and discriminant connected with the root, square root of delta, which defines indirectly the three cases. So each of the cases have their own roots in its own nature. So hence, the significance of delta is to identify the nature of roots, decides the nature of roots. The three different cases as we are taken here. So let's take each of the cases with the three cases defined in the previous session with an example problems. So when I have the quadratic equation x squared plus x plus 7 equal to 0, then clearly I have a equal to 1, b equal to 1, c equal to 7, through which my delta is b square minus 4ac, that is 1 square minus 4ac, which gives me 1 minus 27, which is negative 27, and this is less than 0. Therefore, delta less than 0 implies the roots are, with the second case which says that the roots are real and complex and the roots are complex or imaginary is how we get the conclusion from delta. So we cannot have the real roots in case of delta being less than 0. We always get the complex roots where the root of a negative number includes in the root. So for example, I substitute in the formula minus b plus or minus this by 2a. Then I have this minus b, which gives me minus 1 plus or minus root of this entirely being equal to delta gives me the value as negative 27 by 2 times of a, which is 1. Thus, the root of a negative number cannot give a real value. Therefore, this whole of the two roots as obtained in case of this quadratic equation are said to be complex roots. The two complex roots being minus 1 plus root of negative 27 by 2 and minus 1 minus root of negative 27 by 2 are the two complex or imaginary roots identified in case of this. The case 3 of the discriminant significance. Next, let me take another example. Say x squared minus 5x plus 6 equal to 0. Then in this case, I identify a equal to 1 and b is minus 5 and c is 6. So here my delta is b squared minus 4ac, which on simplification gives me 25 minus 24 equal to 1. So my delta is 1, which is clearly greater than 0. Therefore, this comes under case 1 of the significance of delta. So delta greater than 0 implies the roots are real and unequal. They cannot be equal. So the roots are real and unequal. So delta greater than 0 implies the roots are real and unequal. Therefore, I have two unequal and distinct roots which are real. So when I want to find the roots using x equal to minus b plus or minus root of delta by 2 times of a, then this on using the formula reduces to the roots 5 plus or minus 1 by 2, which gives me two roots, one given by plus and 5 minus 1 by 2, which on further simplification gives me 6 by 2, which is 3, and 4 by 2, which is 2. Therefore, these two are real roots and are distinct. They are not equal, thus giving me the case 1 of the significance of delta, giving me the two real and distinct roots because delta is simplified to be greater than 0. So in this case, delta is simplified to be less than 0. So I get two real complex or imaginary roots. Here, two real and distinct roots for greater than 0. Now let's see the case 2 of the significance of delta, where I take the quadratic equation x squared minus 4x plus 4 equal to 0. So in this case, my a is 1, b is minus 4, and c is 4. Therefore, my delta is b squared minus 4ac, that is 4 squared minus 4ac, which on simplification gives me 16. So therefore, this gives me 16 minus 16, thus delta equal to 0. Now we all know that this is case 2 of the significance of delta, where delta equal to 0 implies the roots are real and equal. That implies when I have delta simplified to be 0, I get one repeated root when I solve this using the formula. So delta equal to 0 implies the roots are real and equal. That is, when I simplify this using the formula minus b plus or minus root of b square minus 4ac by 2 times of a, then this on simplification gives me minus of minus 4 is 4 plus or minus 16 minus 16 by 2. Therefore, this would be 16 minus 16 is root 0 is again 0 by 2. This gives me 2 roots, 4 by 2 and 4 by 2 is 2 is 2. Therefore, I get one repeated root, which is 2. The roots of this would be 2 comma 2 with this value being repeated again, the case 2 of the significance of delta, thus leading to delta equal to 0 with 2 repeated roots. Now let's see the topic of the session, equations reducible to quadratic form. Sometimes there are some equations which are not directly in the quadratic form, but we need to do some substitutions to then reduce to the quadratic form and then factorize. So let's see some of the example problems which demand for reducing to the quadratic form. To start with an example problem, say I wanted to factorize 7 power 1 plus x plus 7 power 1 minus x is equal to 50. Then I want to factorize this or solve is the question. Then I clearly see that this is not in factorized in the quadratic form, and therefore factorizing this would not be an easy task. So let's attempt to see if I can reduce the given equation into the quadratic form. So for example, 7 power 1 plus x I split using the law of index a power m plus n is a power m times a power n, and this can be written as 7 power 1 by 7 power x because a power m minus n is a power m by a power n, the law of index, which is equal to 50. Now proceeding similarly, I get this to be taking LCM or multiplying throughout with 7 power x, I get this to be 7 power 2x plus 7 equals 50 times 7 power x. So I have multiplied the whole of the equation with 7 power x in this form. So multiplying with 7 power x, I get this to be this 7 power x into 7 power x is 7 power 2x using the law of index, and then this reduces to 7 and this because this gets cancelled, and then 50 times of 7 power x. Now from here, let's rearrange 7 times 7 power 2x and minus 50 times 7 power x plus 7 equals 0. So I bring all terms to the left. Now with this, let's see how I can convert the obtained equation into the quadratic form. So for this, what I do is let 7 power x equal to some t, because this gives me an understanding that so when 7 power x is t, then my 7 power 2x is 7 power x times of 2, which is t square. Therefore, I can write 7 power 2x as 7 power x whole 2 using the law of index a power m is a power m whole times of n is a power mn, and therefore I get this to be this, but this is nothing but t, which is substituted in place of inside the bracket, so the t square. So I have 7 power x is t and 7 power 2x is t square, which I am going to substitute in this quadratic equation, in this obtained equation. So let's see what I get. In the first case, this is 7 times t square minus 50t plus 7 equals 0 is what I get when I substitute these two in the above equation. Now this clearly is a quadratic equation which is obtained to be reducible to quadratic form. Therefore, this equation is substituted with 7 power x equal to 2 after further simplification, and then that gives me a quadratic equation in T. Now it is not a tough task for finding the factors for this quadratic equation, and the factors of this quadratic equation indirectly give me the factors of this given equation. Thus solving the given equation is the intention behind equations reducible to quadratic form. So therefore here let's factorize the 7t squared minus 49t minus t plus 7 equals 0. So I get two values, 7 and 1 over 7, through which I'm going to simplify. So there are two values I got. T is 7 and t is 1 by 7. Now when t is 7, my t is nothing but 7 power x, which I'm going to substitute here because I have this equals this. And in this case 7 power x is 1 by 7, which is 7 inverse, which I can write for this. Now when the bases are equal, the powers are equal, therefore this gives me x equal to 1, and when the bases are equal, the powers are equal, therefore this gives me x equals minus 1. Therefore the solution of this given equations are x equal to 1 and minus 1 is how we understand the equation which is not in quadratic form reduced to the quadratic form by substitution of this in the quadratic integral, and then that gives me the values of x indirectly. This is how we understand equations reducible to quadratic form. Now let's see a theorem through which we understand the common root concept connected with a property. So the theorem says here that the necessary and sufficient condition for the quadratic equations a1x squared plus b1x plus c1 equal to 0 and a2x squared plus b2x plus c2 equal to 0 are the two quadratic equations which I considered, and the theorem states that the necessary and sufficient condition for the quadratic equations this to have a common root is that I have c1a2 minus c2a1 whole square equals a1b2 minus a2b1 times b1c2 minus b2c1 is the condition which I need to prove both as a necessary and a sufficient condition. So let's see how we can derive the proof of the given theorem. Now as we read the statement, we clearly understand that there are two quadratic equations which are given with the condition to have a common root. So because we don't know what a common root is, let's take the common root of these two quadratic equations as some alpha and then proceed with the proof to finally get this equal to this. Now coming to the proof, let alpha be the common root of the quadratic equations a1x squared plus b1x plus c1 equal to 0, a2x squared plus b2x plus c2 equal to 0, which I take as equation 1 and equation 2. Now because alpha is the common root of this equation 1 and equation 2, that means alpha is the root of 1 and 2 independently. That is, when we say that alpha is the root, it must satisfy the given quadratic equation because it's simply the root or the solution of the given quadratic equations. That implies I get a1 alpha square plus b1 alpha plus c1 equal to 0, and a2 alpha square plus b2 alpha plus c2 equal to 0, which I take as 3 and 4. And this is because since alpha is the root of equation 1 and 2. This is because alpha is the root of both equations 1 and 2, giving me this and this. Then what I do is consider b1 times of equation 3, a2 times of equation 3 minus a1 times of equation 4. So here finally what I am doing is I multiply the whole of equation 3 with a2 and multiply the whole of equation 4 with a1 and then subtract. So let's see what we usually get. So when I multiply equation 3 with a2, I get this to be a1 a2 alpha square plus a2 b1 alpha plus a2 c1 equal to 0 is what I get when multiply equation 3 with a2. Similarly, I multiply equation 4 with a1, I get a1 a2 alpha square plus a1 b2 alpha plus a1 c2 equal to 0, and then I subtract these two equations. So on subtraction I get this cancelled because these two are the same terms under subtraction. So finally I take alpha common and I get a1 a2 b1 minus a1 b2 plus a2 c1 minus a1 c2 equals 0. So therefore, if I continue from there, I get this to be minus alpha times of a1 b2 minus a2 b1 equals a1 c2 minus a2 c1, because when I bring here it comes as minus, which can be adjusted for these two terms interchanging. Therefore, when I bring this out here, I get alpha times of a1 b2 minus a2 b1 equals c1 a2 minus c2 a1 is what I get for the given expression. So I take this as equation 5, and then let's see how we can take the other set of simplifying the equation 3 and equation 4. Now similarly, let's see if what happens when I multiply equation 3 with b2 and equation 4 with b1. That is, I consider in my next case b2 times of equation 3 minus b1 times of equation 4, and then see what exactly the subtraction leads to. So when I multiply equation 3 with b2, I get this as a1 b2 alpha square plus b1 b2 alpha plus c1 b2 equals 0, and then from equation 4 multiplied with b1, I get a2 b1 alpha square plus b1 b2 alpha plus c2 b1 equals 0, and then I subtract so that this time this is the common term which gets cancelled. So proceeding as in the previous case, I take this common and I get a1 b2 minus a2 b1 times of alpha square equals plus c1 b2 minus c2 b1 of this equals 0 is what I get when I simplify using the subtraction process. Now, taking this into consideration, I get this to be further simplified as a1 b2 minus a2 b1 of alpha square equals, I bring this to the right, which comes as b1c2 minus b2c1, which I take as equation 6. So I got totally two equations, equation 5 and 6, which I'm going to consider to get this condition. So let's see how we can obtain the condition using this in consideration. Now, these are the two equations which have obtained from multiplying the equations 3 and 4 respectively and then subtracting. So with these two equations, what I do, I just take equation 5 and squaring on both sides of equation 5, I obtain on the left hand side alpha square of a1 b2 minus a2 b1 whole square equals c1 a2 minus c2 a1 whole square. This is clearly when I square on both sides of equation 5. Now I try to use equation 6 in this, is the intention behind. So in this case I can split this as alpha square times a1 b2 minus a2 b1 times a1 b2 minus a2 b1, because this is square which can be split in two different terms, that is equal to c1 a2 minus c2 a1 whole square. The reason behind splitting the two terms of the square is that from equation 6 I have directly alpha square of this as b1 c2 minus b2 c1. So this can be substituted for this. Whole square is what I get when I substitute this here. So rearranging, I get this to be the left hand side of this term is c1 a2 minus c2 a1 whole square is a1 b2 minus a2 b1 into is what we get as the necessary condition. Now, assuming that alpha is the common root, I proved that this equal to this is called necessary condition. Now, assuming that this is equal to this, I prove that alpha is the common root will be the sufficient condition. The reverse process of the necessary condition and its proof. Is how we understand the necessary condition through the proof. Now let's see the sufficient condition of the theorem. Now let's take the sufficient condition, that is assuming that for the given two quadratic equations which are given by equation 1 and 2 in the previous case, we have the condition which states c1a2 minus c2a1 whole square is equal to a1b2 minus a2b1 times b1c2 minus b2c1 is what is the necessary, the sufficient condition out here. Now with this, I prove that there is a common root between two quadratic equations. So to start with the proof, I take two cases where in case 1, I assume with two cases. So let's take the case of, there are two cases through which I'm going to prove the sufficient condition. So in the initial case, I assume that a1b2 minus a2b1 is equal to 0. So using this equal to 0, I prove for the common root, that is the sufficient condition. So because a1b2 minus a2b1 is 0 on the case 1, that implies substitution in this equation gives me c1a2 minus c2a1 is also 0, since we have this condition which we have taken in the sufficient condition. Now with these two conditions, let's see what exactly I get. From the previous assumption of case 1, I get this as a1b2 equals a2b1, and from this I get c1a2 is equal to c2a1. Now, proceeding similarly further, I get this to be A1 by B1 equals A2 by B2 is what? I rearrange these terms. Now from this, I arrange this in the form C1 by A1 equals C2 by A2. So I have got totally two cases of A1 by B1 is A2 by B2 and C1 by A1 is C2 by A2. Now if I assume the given quadratic equation A1x squared plus B1x plus C1 as say A1, B1, C1. To avoid the lengthy simplification of this, I assume this quadratic equation in this form, and then I assume the other quadratic equation A2x squared plus B2x plus C2 as A2, B2 and C2 is what we get. Now if I assume for these two quadratic equations in the triad forms, then therefore from this I get this by taking common of A1, I get this as 1 B1 by A1 C1 by A1. By taking A1 out, each of this gets reduced as 1 by A1 and 1 by A1 of this. So indirectly we assume the quadratic equation in the form with A1 times of 1x squared plus B1 by A1 of x plus C1 by A1. This is written in triad form. Now here I get this B1 by A1, which we have as B2 by A2. If I interchange, can be written as B2 by A2 because A1 by B1 is A2 by B2. Therefore B2 by A2 is B1 by A1 substituted for this using this condition. Similarly, my C1 by A1 is C2 by A2, which comes out in this form out here. So therefore, when I multiply A2 inside, then I get A2 comes out and this reduces to A2, B2 and C2 because each of this is multiplied with A2 where A2 gets cancelled here and this 1 times of A2 comes in this way. Again bring back A2 inside, I get 1 B2 by A2 and C2 by A2, that is taking A2 outside the bracket. Now as I see this, I see that this is A1 by A2 of A2 B2 C2 is A2x squared plus B2x plus C2. Therefore, I have the first quadratic equation which can be expressed as a multiple of the second quadratic equation. This making us understand that therefore A1x squared plus B1x plus C1 equal to 0. Therefore, by taking this quadratic in this form, I have an A1x squared plus B1x plus C1 equal to 0. Then indirectly this A1 by A2 times of A2x squared plus B2x plus C2 will be equal to 0, where this brought to the right gives me if and only if A2x squared plus B2x plus C2 equal to 0, assuming that A1 by A2 is not equal to 0. Therefore, this makes me understand that when this is 0 implies the two given quadratic equations 1 and 2 have same root is how I understand the case 1 of the sufficient condition. But it's very important to identify here that I can take A1 common with A1 coming in the denominator because A1 is not equal to 0. When I have A1 equal to 0, the whole of the quadratic equation reduces to linear form. Therefore, in this case, A1 is not equal to 0. And in this case, A2 is not equal to 0. So each of A1, A2 is not equal to 0. Similarly, we have the case 2 through which we can prove the given sufficient condition of the theorem. The case 2 of the sufficient condition, where I reconsider the equation which I have obtained from equation 5 of the previous continued theorem. So reconsidering equation 5, I have this already from the previous session. That implies I get my alpha as C1A2 minus C2A1 by A1B2 minus A2B1 is what I get as this new function when I bring this to the right. Next, now since alpha is the root of a1x squared plus b1x plus c1 equal to 0, therefore I have this satisfying the equation as a1 alpha squared plus b1 alpha plus c1 equal to 0, since alpha is the root of the given quadratic equation. Now with this being the root of, I substitute the value of alpha which I have here in this equation, so that I get a1 times alpha, which is c1a2 minus c2a1 whole square by a1b2 minus a2b1 whole square plus b1 times of alpha, which is c1a2 minus c2a1 by a1b2 minus a2b1 plus c1 equals 0, because this value is substituted in this equation. Now from the sufficient condition, I have this c1a2 minus c2a1 whole square with its own formula. So from sufficient condition, I have c1a2 minus c2a1 whole square is nothing but a1b2 minus a2b1 into b1c2 minus b2c1 by denominator, which is a1b2 minus a2b1 whole square, where this of whole is substituted with this from the sufficient condition. Then next, this is written as it is c1a2 minus c2a1 by a1b2 minus a2b1 plus c1 equals 0. Now we see that one of the common factor is cancelled from both numerator and denominator. So proceeding, I get this to be a1 times b1c2 minus b2c1 by a1b2 minus a2b1, which is the simplified form of this after cancelling one of the common factor. Next, I get this b1 times c1a2 minus c2a1 by a1b2 minus a2b1 plus c1 equals 0. Now I want to simplify the entire expression on the left hand side by simply taking the LCM. So let's see what happens when I take the entire LCM. So my whole of the LCM is a1b2 minus a2b1, which on simplification gives a1 times b1c2 minus b2c1 plus b1 times c1a2 minus c2a1 plus c1 times a1b2 minus a2b1 equals 0, because we have this entirely taken in the LCM, where the LCM is a1b2 minus a2b1. Now when I expand this, each of the term through the brackets, the expansion of brackets give me a1 b1 c2 minus a1 b2 c1 plus, arranging in the form ABC, a2 b1 c1, and this becomes minus a1 b1 c2, then this in the form a1 b2 c1 minus a2 b1 c1 whole of a1 b2 minus a2b1 equals 0 is what we get. Now, when I see this, a1, b1, c2 and a1, b1, c2 are similar, so they get cancelled. Similarly, a1, b2, c1 and a1, b2, c1 plus and minus get cancelled, and a2, b1, c1 and a2, b1, c1 get cancelled, so that I get this to be equated to, I get this entirely equated to 0, identically equal to 0. That means what we have got is the correct root cut. So from here I can make it that when I substitute, alpha will be the root, because if I assume that alpha is the root of the quadratic expression, then I get identically 0 equal to 0. That implies alpha satisfies the quadratic equation a1x squared plus b1x plus c1 equal to 0. That implies alpha is the root of this quadratic expression. So this is how we prove that alpha is the root of the given quadratic equation. Similarly, proceeding in the similar manner, I can prove that alpha is also the root of the other quadratic equation, which is a2x squared plus b2x plus c2 equal to 0. And then finally, alpha is the common root. So similarly, we have alpha satisfies the quadratic equation, the other quadratic equation a2x squared plus b2x plus c2 equal to 0. Therefore, since alpha satisfies, or alpha is the root of both the quadratic equations, therefore we say that alpha is the common root of the two quadratic equations. Which proves the sufficient condition of the theorem. Assuming on the given condition, we have proved in the sufficient part that alpha is the common root. This is how we understand the theorem, both through the necessary and sufficient condition. So let's see some special cases of the quadratic equations. So we have seen the general quadratic equation, which is in the form this. This is called the general quadratic equation. Now, there are three different cases which I'm going to consider here in the special cases. One is if I reduce the given quadratic equation in the form this, that is when b is 0. And secondly, I take the second case where my first and second is same, is what I take in the second case. So let's take the three special cases for the general quadratic equation ax squared plus bx plus c equal to 0, where my first case is taken in the consideration of ax squared plus c equal to 0, and my second case is ax squared plus bx plus a equal to 0, where this and this are same. And thirdly, I take a greater than 0. Then let's see what each of the three special cases conclude in their own understanding. Now coming to the initial case, clearly here I identify that b is 0, and of course my a is not equal to 0 is how we understand this. So in this case, my sum of roots, if my roots are alpha and beta, we all know the general representation of roots is alpha and beta, then we know that sum of roots is negative times coefficient of x, which is not existing here, by a, which is 0, and product of roots is c by a, is what we get. Therefore, whenever I have the quadratic equation in the form ax square plus c equal to 0, or a quadratic equation doesn't have an x term, then the roots of this will differ by same, because alpha plus beta equal to 0 implies beta is minus alpha. The roots differ by a sign. So the roots differ by a sign, but the values are always same. So beta is always minus alpha for these kinds of quadratic equations. Similarly, when I take the special case, the case 2 of considering the quadratic expression or equation, in this case I have taken the first and last is same. So assuming that a is not equal to 0, then in this case my sum of roots alpha plus beta is minus b by a, and product of roots is c by a, that is a by a, because my c is a. In this case my c is nothing but equal to a, therefore I get this to be 1. So this concludes that when a quadratic equation is in the form of ax square plus bx plus c, where the first and last terms are same in their value, then I have beta is 1 by alpha. That means the roots are reciprocal of each other. The roots are reciprocal of each other is how we understand the second case of the quadratic equation. Thirdly, let's consider the third quadratic equation, which is in its general form ax square plus bx plus c. Now in this case I have taken the special case of a being positive. So if a is greater than 0, that is if a is positive, that implies my sum of roots is given by minus b by a. And the product is given by c by a, and of course a not equal to 0 is how we take into consideration. Now in this case we will have an interesting case which arises where we compare between the quadratic expression and the value of a. So how we are going to do that is what we are going to discuss in the third case. So from this, if I assume that a is greater than 0, let me take the product of the roots, which is c by a. Now here I clearly identify that the product of roots, if it is positive, if I take the first case, if product of roots is negative, then if I take the product of roots is negative, then a being positive, obviously c must be negative. So we derive the sign of c based on the nature of the product of roots. Therefore, if product of roots is negative, that implies c must be negative, since a is positive, is how we conclude in this. Similarly, if my product of roots is positive, then in this case, then let's see what happens. If the product of roots is positive and a is greater than 0 is the case I have taken, then c must also be positive, is how we compare the sign, we measure the sign of c based on the sign of a and the product sign. So if product of roots is positive, that implies c must be positive, since a is positive or a is greater than 0. Therefore, c must be positive since a is greater than 0, is how we understand the case 3. So therefore, the product of roots define the sign of a and c. That is, if a and c are positive, then the product of roots is positive. If a and c are of opposite signs, one being plus and one being minus, either way, then the product of roots will be negative, is how we conclude connecting the values of the signs of a and c with the product of the roots, because alpha beta is c over A is how we conclude the sign change. So with these three different cases, we understand that as the quadratic equation changes, the properties or the roots will try to behave in a different way. In the first case, the roots differ by a sign. In the second case, the roots are reciprocal of each other. In the third case, the product of roots define the sign of A and C. This is how we study the different natures of roots, which we are going to discuss here. But the most important note here is that if one of the root is real, the other root also must be real. It is not that one root can be real and the other root can be unreal, but the possibility is that only both the roots must be real. Therefore, if you get one of the root as real, then obviously the other root also must be a real value, but not an imaginary or a complex value. Now let's take the standard quadratic equation, which is given by f of x equals ax squared plus bx plus c equal to 0. Now if I say the roots of this quadratic equation are alpha and beta, then I'll derive some interesting properties from this general quadratic equation with its roots alpha and beta. Now let me start with the first formula, where if I say my c is not equal to 0 and of course a not equal to 0 and alpha beta are non-zero roots, then in that case, if I take the function f of 1 by x, for the given function f of x, if I take the function f of 1 by x, will have the roots 1 by alpha and 1 by beta. This kind of a function will directly have the roots 1 by alpha and 1 by beta. Is how we understand this property. Similarly, if I have, say, f of x minus k, if I consider f of x minus k equal to 0, then this function will have the roots alpha plus k and beta plus k directly. So we have a formula which says that if I subtract k from the function x value, then the whole quadratic function changes, and immediately that new quadratic function will have the roots alpha plus k, beta plus k, is the direct property we identify here. Thirdly, we identify if I change the sign as minus x, then the roots of this function will be minus alpha and minus beta, because the roots will also change with sign as the value of x changes with sign inside f. That is, f of minus x equal to 0 will have the roots minus alpha and minus beta. Next, if I take k not equal to 0, then in this case my f of, if I divide with k, then I have the new roots which we are going to identify here. So when I divide k to x, then the roots of this kind of a function will be in the form k alpha and k beta are the roots which we identify. So this is how we identify each of the properties, the 4 different formulae connected with the respective functions as the roots respectively out here. We take them as formulae and then we derive for various problems which consider each of these cases, the special formulae connecting the quadratic equation and its roots. So let's see one of the theorem which connects the change in signs or is included with sign of quadratic expressions. So the theorem states that if there are 3 constants a, b, c belong to real number, there are 3 real constants a, b, c, and a is not equal to 0, then I have to prove that then the expression, then ax squared plus bx plus c equal to 0, that is the quadratic equation ax squared plus bx plus c equal to 0, has non-real complex roots if and only if the expression ax squared plus bx plus c and a, that is the coefficient of x squared, have same sign for all x belonging to real numbers. So this is the statement through which I'm going to prove. So let's initially start with the statement of the theorem, understanding the statement of the theorem. So it's given that a, b, c are real coefficients and a is a non-zero real number. Then I have to prove that the quadratic equation ax squared plus bx plus c equal to 0 has non-real complex roots only under the condition that they have same sign. That is, if this expression and a have the same sign for all real numbers of x, then the roots of this are directly non-real complex roots. Or if the roots are non-real complex, and then immediately I can say this and this have same sign. This is both the necessary and the sufficient condition. So initially I prove, assuming that this has non-real complex roots, I prove that the expression this and this have same sign, and conversely I assume that the expression and a have same sign. I prove that the quadratic equation has non-real complex roots. So let's start with the first assumption. Now before we start with, it is given clearly that let a, b, c belong to 0 and a be a non-zero real number. Now let ax squared plus bx plus c equal to 0, the quadratic expression, have non-real complex roots. Now we know that when the roots are complex, the discriminant is less than 0. So using the property from nature of roots, this has complex roots implies delta, which is b square minus 4ac, is less than 0, is how we get from nature of roots. So this implies when b square minus 4ac is less than 0, 4ac minus b square is greater than 0, is what we take here. Now we utilize this in the later part of the proof, where I take this as equation 1. So through this equation 1, let's see how we can show that this and this have same sign. So to do that, initially I consider the quadratic expression ax squared plus bx plus c. So the quadratic expression ax squared plus bx plus c, which I considered, I take a common out here. So what happens when I take a common from this entire expression is that when I take a out, this comes as x squared plus b over ax with this. So when a is taken out, the remaining two terms have this in this form. So I am going to make this a perfect square by using the complete square form. So for that, what I do is I multiply this with a times of x squared, which stands as a squared, plus 2 times of b by 2a of x, because I need a squared plus 2ab, which is 2ab. Then b squared is missing because we need to make this a perfect square by using b squared. Now since b squared term is missing, I add and subtract b squared. The b term, which is b by 2a whole square minus b by 2a whole square plus c over a, is what I get, such that this entirely can be reduced to the perfect square using a plus b whole square. So to continue with how we can just expand this with the formula. Now let's try to expand with the formula. Now this becomes a times of a plus b whole square, that is x plus b by 2a whole square, and this on simplification gives me 4a square is the LCM, and therefore this reduces to minus b square plus 4ac is what I get. So this is what I get when I expand with formula. Now let me take this a to the left so that this comes out as by a, and this is nothing but x plus b by 2a whole square plus 4ac minus b square by 4a square, which I take as equation 2. Now as I see here, interestingly, I see that this is a square, and we know that all squares are positive, so this will be a positive term because all squares are positive, and 4ac minus b square is positive from equation 1 which we have taken. So this is positive, and this again is all squares which is positive, this from equation 1, and this is because all squares are positive, and here this also is a square, so any square term will be a positive term. So positive, positive, and positive when added gives me a positive term. Therefore I see that implies ax square plus bx plus c by a is a positive term, since each term of right hand side is positive. That is, each term of right hand side of equation 2 is positive. Therefore this entirely is positive, and therefore indirectly this term is positive, this being positive and this being equal to this. Now this being positive implies that the possibility of this fraction being a positive number is that they should be of same sign, because if one of them is plus and one of them is minus, then the fraction becomes a negative value. Therefore the rule says that if a by b is positive, implies a and b are of same sign. They should be either both positive or they should be both negative, but they cannot have opposite signs. Opposite signs make this negative. So therefore when a by b is positive, that implies a and b are of same signs is the property which we have identified in the general properties of fractions. Therefore this by this being positive implies that a and b are of same signs, that is, this and this are of same signs. Ax square plus bx plus c and a are of same signs for all x belonging to R. So this proves the necessary condition of the theorem, where I assumed that the roots are complex, and I have proved that this and this have same signs. Now in my converse of the theorem, I assume that the expression and a are of same sign, and I prove that the given quadratic equation has the complex roots. So let's see how we can prove out the converse of the given theorem. So conversely, I consider that ax square plus bx plus c and a have same sign is what I consider for all x belonging to real numbers. Now using this, I had to prove that the roots of this quadratic equation are complex, non-zero complex numbers. Now since the expressions this and this have same sign, using the previous property, the fractional representation of this by this will always be greater than 0 for all x belonging to R, because when the two expressions are of same sign, their fractional representation will be greater than 0, cannot be of opposite signs. Therefore this must be greater than 0. Now, as we know that this has already been simplified from equation 2 as x plus b by 2a whole square plus 4ac minus b square by 4a square, which is greater than 0. This is purely obtained from equation 2, which we have already derived in its perfect square form. So therefore, substituting this for this from equation 2, I get this equal to the entire term greater than 0 from equation 2. Now, if I see this, I observe that this all squares are positive, so this is positive, this must be positive, and this obviously must be positive because this is positive. When the whole expression is positive and each of these two are positive, then obviously this must be positive. Therefore, when I take this term, I get that now since the whole expression is positive, that implies 4ac minus b square is positive is what we get. Since each of the term is positive and the whole expression is positive, therefore one term which is particularly here also must be positive is what we get here, which gives me the conclusion that if 4ac minus b squared is greater than 0, then b squared minus 4ac is less than 0 when I interchange this with this. That is nothing but delta, which is less than 0 because b squared minus 4ac is referred as discriminant delta. Now, when we connect with the nature of roots, when delta is less than 0, we assume that implies the roots of the quadratic equation ax squared plus bx plus c equal to 0 are non-zero complex roots, which proves the sufficient condition. Therefore, the necessary or the theorem with its necessary and sufficient condition has been proved respectively for the assumption of the given quadratic equation having complex roots and proving that this and this have same sign, and then assuming that this and this have same sign, we have proved that the roots of the given quadratic equation are non-zero complex roots, is how we understand the theorem with both its necessary and sufficient condition. Now let's take the extension of the previous theorem which we have discussed connecting with change of signs. Now here the extension is with reconsideration of equation 2 which we have obtained in the previous case as ax squared plus bx plus c by a was derived to be x plus b by 2a whole squared by 4a square is what we have obtained. Now, in this case, if I assume that if the roots of ax squared plus bx plus c equal to 0 are real and equal, equal being the condition, then we obtain that when the roots are real and equal, then we have delta, which is b squared minus 4ac is equal to 0. We all know this by nature of roots. If the roots are real and equal, then delta, which is this, is equal to 0. So let's see what happens in the case of the roots being real and equal when substituted into this. So therefore, I obtain ax squared plus bx plus c by a is x plus b by 2a whole square, because the whole of this gets vanished when I substitute b squared minus 4ac equal to 0. 0 by 4a squared becomes 0, and hence we get only this. Now, that implies the expressions this and this will have same sign if this entirely is positive, but this is positive only when x is not equal to minus b by 2a, will have same sign if x plus b by 2a is not equal to 0. Because if this is 0, the whole of this becomes 0, and then it is difficult to predict the signs of the numerator and the denominator. So for this to be strictly greater than 0, this has to be not equal to 0. That is, x is not equal to minus b by 2a. Therefore, I understand here in the extension of the theorem that the given quadratic equation will have, if the quadratic equation has real and equal roots, then this and this will have same sign if x is not equal to minus b by 2a. This is strictly the condition when the roots are real and equal, is how we extend the theorem to understand the further properties of roots being real and equal. Now let's see the theorem which is supported from the previous theorem which we have discussed. So this also is an extension of the previous theorem to understand the further properties which are connected with quadratic equations and the signs of curves. So the change of signs here, let's start with the statement of the theorem. So the statement of the theorem states that let a, b, c be three real constants and a not equal to 0 such that the quadratic equation ax squared plus bx plus c equal to 0 has real roots alpha and beta with alpha less than beta then I'm going to prove that with these conditions of this quadratic equation having real roots alpha and beta with alpha less than beta, then initially I prove that for alpha less than x less than beta, that is when x lies between alpha and beta, we have ax squared plus bx plus c and a have opposite signs. So we had to prove here that when x lies between alpha and beta, then this expression and a will have opposite signs. Similarly, for x less than alpha and x greater than beta implies this and this have same signs, is what we are going to prove. So there are two cases which we are going to prove here, whereas the case 1, when x lies between alpha and beta, this and this have opposite signs. When x lies outside of alpha and beta, then this and this have same signs, is how we are going to prove. So let's see how we can prove that with the proof followed. So clearly it is given that a, b, c are real numbers and a is not equal to 0, then alpha beta are roots of ax squared plus bx plus c equal to 0 implies I can write ax squared plus bx plus c as clearly a times of x minus alpha into x minus beta, where I assume alpha is less than beta. So with the assumption that alpha is less than beta. So using this, we are going to prove the sign change, opposite signs and same signs connected with this. So let's see how we can do that with. Initially, to start with, let me reconsider the above expression in the form of by a is x minus alpha into x minus beta, because this is the expression which helps us in understanding the signs. Because we need to identify the opposite or same signs, we divide this with this, because the fractional representation helps us in identifying the same signs or opposite signs. So therefore, we have obtained the expression as ax squared plus bx plus c by a is obtained as a times of x minus alpha into x minus beta, which I took as equation 1. Now using this, let's see how each of the cases can be proved for. So initially, to start with case 1, I have alpha less than x less than beta, that is x lies between alpha and beta. So using this, let's see how we can prove for this and this with opposite signs. So alpha less than x less than beta can be split as this and this in the form that alpha is less than x and x is less than beta. The first pair and the second pair are split in the inequality. Now here, this is alpha less than x implies x minus alpha is greater than 0, and x less than beta implies x minus beta is less than 0. So this proves that this is positive and this is negative, because greater than 0 and less than 0, and positive into negative is negative. Therefore, if I combine them, x minus alpha into x minus beta will be negative, because plus into minus is minus. We all know that property. Plus times minus is minus. So plus times minus is minus. So this being negative, we know that, oh, this is not a, but a is already here. We know that x minus alpha into x minus beta is indirectly this whole of expression. So in place of this, I substitute this, because these two are equal. Therefore, substituting for the left hand side, I get this to be ax squared plus bx plus c by a, which is less than 0. This is strictly from equation 1 is what I get. Now this makes us clearly understand that if numerator by denominator is negative, that means both should be of opposite signs but cannot be of same signs, because if I have minus 5 over minus 3, this becomes positive, or 5 times of 3 also becomes positive. But if one of the sign is changing opposite signs, then it becomes a negative, or minus 5 over 3 also becomes a negative number. So with these examples, we assume that when this whole of the expression is negative, then numerator and denominator must be of opposite signs, as supported with these examples. That implies the expression and a will be of opposite signs is what we conclude. Assuming that x lies between alpha and beta, then this is the case. This and this will have opposite signs. Similarly, let's take the case 2 and see if we can get this to be of same signs or opposite signs. So proceeding similarly as case 1, let's continue with case 2. So let's take the case 2, which says that x is less than alpha or x is greater than beta is what we're going to consider and prove for the sign change. So initially, to start with x less than alpha, and finally with x greater than beta, I get x less than alpha implies x minus alpha is less than 0 is what we get here, and x greater than beta implies x minus beta is greater than 0 is what we get out here. Now let's see the case 2, where x is less than alpha or x is greater than beta, where I split initially with x less than alpha and then with x greater than beta, and see with each of the cases. Now as I know that alpha is less than beta in either of the cases, let's initially proceed with this and see what exactly I get. Now x is less than alpha and alpha is less than beta implies x is less than alpha less than beta. X less than alpha here and alpha less than beta out here. So with this, I understand that x is less than alpha and x is less than beta in case of this first case. Therefore, I get x minus alpha is less than 0 and x minus beta is also less than 0 in the initial case. Now let's see the second case of x greater than beta and alpha less than beta. So x greater than beta and x and beta, that implies I have this as beta less than x, but alpha is less than beta. So I have this to be when beta is less than x from this equation, x greater than beta, beta less than x, and alpha less than beta from here implies beta is less than x. Therefore, alpha is less than x. Therefore, in this case, I get two conditions: x is greater than beta and alpha is less than x. So are the two cases which I get here, such that when I simplify, I get x minus beta greater than 0 and x minus alpha is greater than 0, because alpha minus x is less than 0, x minus alpha is greater than 0, and this is greater than 0. So proceeding with this two cases of considering, initially I get both of them as negative and both of them as positive. Thus, when I multiply x minus alpha times x minus beta, when both are negative, the product of negative and negative is positive, because since minus into minus is plus. We all know that. This is positive and this is positive, so plus into plus is plus. Therefore, I get this x minus alpha into x minus beta is greater than 0 when I combine the product of these two, since plus into plus is the case here. Now, I try to substitute this for this and see that the two expressions will have same sign, because when I consider ax square plus bx plus c by a will either be positive or positive. In both the cases, this is positive or greater than 0 implies that when the numerator by denominator is positive, these two must be of same sign. Both must be minus or both must be plus. We cannot have 1 plus 1 minus or 1 minus and 1 plus. The possibility of this is positive implies and A will have same sign, is how we understand the quadratic expressions with change of signs. So therefore, for case 2 they have same sign and for case 1 they have opposite signs, is how we understand. Now let's see the maximum and minimum values of quadratic function or a quadratic equation. Now in this case, we have a very deep relation between the sign of a, that is the coefficient of x squared, which we denote with a, and the extreme values, that is the maximum and minimum values. Say for example, I take the quadratic function y equals f of x as general quadratic equation ax squared plus bx plus c, then I always have a relation between this a, which is coefficient of x squared, and the extreme values, that is max and min of this function. The highest and the lowest value of this function is always related with sign of a. Decides the extreme values of the quadratic function, is how we understand the relation between sign of a and the quadratic function. So let's see through the supported theorem how the sign of a is related to the extreme values of the quadratic function, the max and min of the given quadratic function. So let's see the statement of the theorem supporting the sign of a and the extreme values. The theorem states that there are three constant real coefficients a not equal to 0 such that y equals ax square plus bx plus c. Then I had to prove that if suppose I have a greater than 0 implies, for this sign of a being positive in the first case, implies the quadratic function. So when a is positive implies the quadratic function y equals ax square plus bx plus c has absolute minimum. So here we relate with a greater than 0 I get a minimum value, and for a less than 0 of course with maximum value, is how we connect this coefficient of x square, that is a, with its sign related to minimum. A positive, function minimum; a negative, function maximum. So therefore, for the first statement which says that a greater than 0 implies the quadratic function y equal to ax squared plus bx plus c, the general quadratic function has absolute minimum. And not only that, to add with further property, we need to prove that has absolute minimum at x equals minus b by 2a, and I had to prove that my minimum value is nothing but 4ac minus b squared by 4a. So I need to prove that my minimum value is this, and it is minimum at x equals minus b by 2a. Are the two things which I need to prove in my part A of the theorem. Similarly, my part B has to be proved with stating that if a is negative, that is if a is less than 0, that implies the quadratic function y equals ax square plus bx plus c, as taken in the previous case 2, has absolute maximum. Here being absolute minimum, here it is absolutely maximum for a less than 0 and absolute minimum for a greater than 0. Has absolute maximum at x equals minus b by 2a, and maximum value is 4ac minus b squared by 4a. Is the same case as we obtain for the minimum condition, is what we are going to prove in the statement of the theorem. So let's start with the continued part of the proof of the above theorem. Now to start with the proof, let's start with the general quadratic function. So we have already considered the general quadratic function as y, which I represent as f of x, and which is nothing but ax squared plus bx plus c, with a, b, c being the real coefficients, and of course a not equal to 0. Now also we have seen that this quadratic function, when simplified in the previous theorem, was further simplified with the complete square form when I take a common as a times of x plus b by 2a whole square plus 4ac minus b square by 4a. Therefore, my f of x can also be further simplified into complete square in this form, as this was already proved in the previous theorems. So let me take this simplified form as equation 1, through which I am going to achieve the proof of the given theorem. Now, initially, to start with, the first condition, I have a greater than 0. Therefore, let a greater than 0 and prove for the part A of the theorem. So when a is greater than 0, I clearly see here that from equation 1, I clearly see that a is greater than 0 and x plus b by 2a is also whole square is also positive. So this being positive since a is greater than 0, and this is positive since all squares are positive. Therefore, the whole of this term is positive because a greater than 0 and squares are greater than 0. So this into this is overall a positive value. Therefore, that implies f of x can be written as a positive value, some positive value which is not a fixed value out there, plus 4ac minus b squared by 4a. Now, as I also observe here, I see that this is the term independent of x, which I write separately out here. Therefore, I get a positive value plus 4ac minus b squared by 4a when I simplify through this and this. Using the condition of a greater than 0, this being positive plus this. So this makes me understand that f of x is always greater than this because there is some positive value added to the given quantity. So which makes us understand that f of x should obviously be greater than or at the most equal to 4ac minus b squared by 4a, because there is some value, positive value added to the quantity this for getting f of x. Therefore, this must always be greater than this always being smaller quantity than f of x with positive value added out there. So this is greater than or equal to this is what we get in the initial case. So f of x is greater than or equal to this. Similarly, let's also continue with seeing what happens when I take x equals minus b by 2a. This is strictly greater than, and I will also prove for equality condition in the second case, for which I take this as equation 2, where I have proved that f of x is greater than 4ac minus b squared by 4a. Let's take equality condition in the continued proof. Now let's take x equal to minus b by 2a. For x equals minus b by 2a, now substituting in 1, I get f of x is 4ac minus b squared by 4a, which I get through substitution of x equal to minus b by 2a in equation 1. Now, when I see equation 2 and 3, I see that from equation 2, I have f of x. Therefore, when I combine equation 2 and 3, I get from 2 and 3, f of x is strictly greater than or equal to 4ac minus b squared by 4a is what we get. Now this makes us clearly understand that the y value at the most is greater than or equal to this. That means this must obviously be the minimum value, because any value you take for f of x, this always greater than or equal to at the most this. That means this acts as the least value for the function f of x. That implies 4ac minus b squared by 4a is the least value of the quadratic function ax squared plus bx plus c. Every other value is greater than or equal to this. This is the least, and hence this is the minimum value, which proves that implies f of x equal to 4ac minus b squared by 4a is the minimum value of the function of this, and it is minimum at x equal to minus b by 2a. So this is how for a greater than 0 I get the minimum condition in this form, supported with the proof in the above theorem. So for f of x equals, this is the minimum value of this, and x at x equal to minus b by 2a for a greater than 0. That is, this is the minimum value and the function is minimum at x equals minus b by 2a. So x value and y values at the minimum point are given by this. Therefore, when I write the minimum point ax square plus bx plus c for a greater than 0 is given by minus b by 2a, and 4ac minus b square by 4a is how I write the minimum value of the function. Is given by these coordinates, is how we understand this. So let's see how we connect this with the graph of the quadratic function. Now the part B of the theorem is using the condition of a less than 0. That is, what would be the case when a is negative. So when it comes to the part B, I assume that a is less than 0, that is a is negative, and see how we can proceed with the proof of this theorem. Now when I take a less than 0, I clearly see that this function has a less than 0, which is negative, all squares are positive, and then I have some quantity multiplied with this. But negative into positive is again a negative value plus this. That implies my y equals f of x will be a negative value plus the quantity 4ac minus b squared by 4a. So here I clearly understand that unlike the part A of the theorem where I got positive value plus the fixed 4ac minus b squared by 4a, in this case of a less than 0, I have negative into positive, which is negative value plus 4ac minus b squared by 4a. So when I add a negative value to the quantity, it obviously reduces. That means f of x is always less than or equal to this, because there is a negative value added but not the positive value. Adding of a negative value implies reducing the quantity by some units. So in this case, because we are reducing the quantity f of x by adding negative value to this, implies mathematically we have f of x is less than 4ac minus b squared by 4a, which I take as equation 4. Now as I see here, this is less than this. Let's see how equality can be obtained. What happens when I get equality? When, on what cases do I get equality is what we're going to see here. Now let's see what happens when x is minus b by 2a. So even in this case, I see that for x equals minus b by 2a, I have f of x equals 0 plus 4ac minus b squared by 4a, because this reduces to 0 when I substitute x equal to minus b by 2a, and this finally reduces to this by 4a, which I take as equation 5. Therefore, combining equation 4 and 5, I see that, therefore, combining equation 4 and 5, I clearly get f of x is strictly less than or equal to 4ac minus b squared by 4a. So this clearly makes us understand that every value of f of x is less than or equal to this. So this stands as the highest. So this implies 4ac minus b square by 4a is the greatest value of the quadratic function ax square plus bx plus c. So this is the greatest value when f of x is less than or equal to. That implies y equals f of x equals ax square plus bx plus c has minimum value, the maximum value, because this is the highest value which it can reach. Therefore, this has maximum value at x equal to minus b by 2a, and the maximum value is given by 4ac minus b square by 4a. Now this is when a is less than 0, is how we understand the concept of maximum and minimum connected with sign of a. When a is less than 0, I get maximum value, which is this, a maximum at this, and when a is less than 0, greater than 0, I get minimum value and then minimum at this. Now, interestingly, there is a very interesting question out there which says that how can the maximum value and the minimum value be same though when a is differing? In part A also we had the minimum value to be 4ac minus b square by 4a, and even in part B we have the maximum value also 4ac minus b square by 4a. Why do they not change is the biggest question. How can both values be same, maximum and minimum? It is because the sign changes the value as obtained. If a is greater than 0, this becomes the least value. If a is less than 0, this becomes the greatest value. As we do some exercise problems, we come to know on how this is understood as why it becomes maximum or minimum, though the formula is same, but the sign changes the maximum into minimum and minimum into maximum, is how we understand this concept. So finally, when I want to find the maximum point on the function, I can write this as for a less than 0, maximum point is given by minus b by 2a, 4ac minus b square by 4a is how we understand the maximum and minimum of a function, the quadratic function. So continued with this, let's see how we understand this with the graphs. The graphical understanding of this theorem is equally very important because that makes us understand the concept more deeper. So let's enter into understanding the theorem through the graphical understanding. So let's connect the theorem with the graphical understanding because we need to understand this more through the graphs than the analytical or the algebraic solving. Now the theorem had two basic important cases. One is a greater than 0 and a less than 0. So let's divide the two cases of the theorem into one being that the quadratic function has a greater than 0 and the other is a less than 0. Now we all know that a quadratic function is a parabola. So a parabola which is either this or this shaped. So a quadratic function has the shape of a parabola. This is upwards and this is downwards, is what we discussed in the previous sessions of the quadratic function. Now since a quadratic function on graphing is a parabola, now clearly we know that if a is greater than 0, the parabola is downwards, and when a is less than 0, the parabola is upwards. So this is very important note we make, that in this case the parabola is downwards, and for this the parabola is upwards. So as I see this, I clearly see that now since the quadratic function is downwards for a greater than 0, I always see all the points which are going down are the least points, but as you go on to the top, the values start increasing and reach to the highest, which is the maximum value. So this is maximum when a is greater than 0. Now here we see that there are two cases. One is a greater than 0 and a less than 0, as we have seen that a quadratic function is a parabola when I graph either a parabola which is upwards or which is downwards, in this case being upwards and in this case being downwards. So we have learnt in the previous sessions of the quadratic equations and functions that when a is greater than 0, the parabola is always upwards, is how we connect the a with the quadratic function. And when a is less than 0, the quadratic function is downwards. It's a downward parabola for a less than 0, and this is an upward parabola for a greater than 0. Now, as I clearly see here that the values are going on the top, so as we come down, the values start decreasing on the quadratic function. So therefore, as the values when coming down decrease, they tend to come to the least, which is the minimum value which is identified here. So this point will give me the minimum value. This is the minimum point, which is given by the formula minus b by 2a and 4ac minus b squared by 4a is what we get as the minimum point, in this case being a greater than 0. Now, as I switch on to the second case, I see that as the points are moving to the top, they reach, and the values increase and reach to the highest, where this point is called maximum, because this has the maximum point, and thus given by the formula minus b by 2a 4ac minus b squared by 4a, which I get as maximum and minimum, is how I understand for the given quadratic functions. In this case, this quadratic has the maximum, in this case it has the minimum. Is how we understand the maximum or minimum based on a less than 0 and a greater than 0. Now, also it is very important to know that in this case there is no maximum value, because as you go to the top, it goes till infinity. There is no end to the parabola as you proceed upwards. In case of a greater than 0, this goes on, and this goes on till infinity. Therefore, there is no maximum value when a is greater than 0. Similarly, in this case, as you go down, and as you go down, it goes till minus infinity. That is, there is no minimum value out here. It goes till infinity. Therefore, in this case, there is no minimum value for a greater than 0, is how we understand equally the minimum value and the maximum value of respectively a less than 0 and a greater than 0. So let's see what is the vertex and axis of symmetry of the quadratic functions. That is, obviously with two different cases. One is a greater than 0 and next a less than 0, as in this case I have the parabola which is upwards, and here a parabola which is downwards, as we all know here. Now here we know that the coordinates of this minimum point, which the graph turns, the maximum or minimum points are called the vertex, the vertices. So for example, here the point we all know is minus b by 2a and 4ac minus b squared by 4a is the minimum value which I have obtained in my previous case. But what do you mean by vertex of a graph is the biggest question. The vertex is the point where the graph turns. Say for example, the graph is going in one direction. Immediately after reaching here, it changes its direction. All of a sudden, it takes a turn to the other side. So exactly the point where the graph turns is called the vertex. So let's see where we identify the vertex of this graph. So let's start approaching from here. As I go here, I go immediately, then I see that after reaching this point, immediately I take a turn. So the point where the graph turns is called vertex. Therefore, here exactly at this point the graph turns, and hence this is the vertex. We all know it is minus b by 2a and then 4ac minus b squared by 4a is the vertex which we obtain. Now in these two cases, I get the coordinates this and this, through which I understand the vertex. So vertex of the parabola with a greater than 0 is this, and the vertex of the parabola with a less than 0 is also this, only with sign of a differing in the first and the second case. Now what do you mean by axis of symmetry? Axis of symmetry is the line along which the two sides of the graphs are symmetric. That is, it acts as the mirror line. That is, when I draw that line along the parabola, exactly I need to get the mirror image. So therefore, let's see where is that line exactly on this parabola through which I get the mirror image or the reflection of one on the other. So symmetrical shape is obtained when I draw a line straight towards this, passing through x equals minus b by 2a. So a vertical line x equal to minus b by 2a which passes through the parabola is called axis of symmetry, is how we understand. So axis of symmetry is x equals minus b by 2a because this line parallel to y-axis and passing through the parabola will be the line which exactly passes through the middle of the graph, and hence this part is symmetric about this part. It is exactly symmetric about the other side, is how we understand the symmetricity through the line x equals minus b by 2a. So similarly, I identify that if I draw a line x equal to minus b by 2a on to this parabola, also equally I get the graph which is symmetric of this. So this part is exactly symmetric about this. So this also is the axis of symmetry for the given parabolas, respectively for a greater than 0 and a less than 0. So finally, the outcome is a vertex is a point which is a point on the graph where the graph exactly turns. So these two are the vertices, and axis of symmetry is the line where the graph is exactly symmetric on either sides. So here being vertex is this and the axis of symmetry being this for the given parabola. So infinity cases are the most important cases of identifying the quadratic function, never to be neglected with infinite cases. So let's see what happens when x tends to infinity or minus infinity. Where does the function or f of x tend to for x tending to plus or minus infinity? This is what we're going to discuss in the session. So with infinity cases, there are two different cases through which I identify. One is for an upward parabola. If suppose I take upward, of course in this case a is greater than 0, and in this case I take a less than 0. So these are two cases which I have identified. One is a greater than 0 and the other is a less than 0. So in this case, let's see what happens when x tends to infinity or minus infinity. Initially, I start with this. As I see here, x tends to plus infinity implies x is going towards infinity. Let's see what happens to y value. So as I go with the infinite distances, I see that when x reaches here, y reaches here. And when x reaches here, my y equally reaches here. That means I see that when I go more further, it goes here. So as I see that as x is proceeding towards right, y value is going upwards, is what I clearly see with the first three initial points of A, B and C. Therefore, if I imagine or visualize going at infinite distance on x, my corresponding y comes at infinite distance on y-axis. Therefore, when x tends to infinity, obviously in this case, y must tend to infinity. That implies y equals f of x tends to plus infinity, as can be clearly seen in the graph. Similarly, let me have x tending to minus infinity. So as I see here, with the same case, when I go towards negative side of the function, I clearly see the same case where as I proceed towards left, my y value also increases upwards. But when x tends to minus infinity, y tends to plus infinity, because this is infinity, minus infinity, plus infinity and minus infinity. Therefore, my x tends to minus infinity implies y equals f of x tends to plus infinity, because it is moving upwards but not downwards. Downwards implies minus infinity, upwards implies plus infinity. Therefore, for x tending to plus infinity, f of x tends to plus infinity. When x tends to minus infinity, f of x tends to plus infinity, is how we understand for the graph which is upwards, that is when a is greater than 0. So similarly, let's understand the properties for a less than 0 for each of x tending to plus and minus infinity. Now as I come to the second graph where a is less than 0, the parabola is downwards. Therefore, to start with initial case, x tends to plus infinity implies, that is when I go towards right, let's see what happens to the graph. When x, let me say, is with one fixed value, then this has the corresponding y value here. Then the other point taken here gives me the corresponding y out here. Similarly, I take the corresponding value here. Therefore, for each of the points A, B, C, I observe that as the points are moving towards right, the corresponding points are moving downwards towards y-axis. That means when x tends to plus infinity, if I move somewhere there till infinity, then this moves down somewhere at minus infinity, because this is plus infinity and minus infinity, and this is plus infinity and this is minus infinity. Therefore, y tends to negative infinity in case of this. Therefore, this implies y equals f of x approaches to negative infinity, is how we understand the property for a downward parabola. Similarly, when I take x tending to minus infinity, that implies y is equal to f of x. As I can see here, when I go towards left, it is going again towards minus infinity. Therefore, for x tending to minus infinity, y is equal to f of x also tends to minus infinity, is how we understand the properties of a greater than 0 and a less than 0 in case of infinity plus or minus infinity. X tends to plus infinity implies x tends to plus or minus infinity implies y tends to plus infinity. X tends to plus or minus infinity implies y tends to minus infinity. Quadratic inequations is the topic for the session. In all these days, we have been discussing about quadratic equations or quadratic functions where the function was equated to 0 and then factorization and various other properties. Now, in this session, we are going to discuss about quadratic inequations. Now, what is the difference we find between equations and inequations is the biggest question here. So, let's reintroduce the quadratic equation and then come back to how we exclusively define the quadratic inequations. So, to come with the general quadratic equation, y equals ax square plus bx plus c, if this is equated to 0, I call this as quadratic equation. Ax square plus this equal to 0. Of course, with a, b, c belonging to real numbers and a not equal to 0. Now, when this is equated to 0, we call this as quadratic equation. Now, if I remove this equality and replace with greater than or equal to, less than or equal to, I get a quadratic inequation of 4 different cases: greater than or equal to, less than or equal to. So therefore, there are 4 types of quadratic inequations which we identify, one being ax square plus bx plus c, which is greater than 0, coming to the first case, and ax square plus bx plus c, which is greater than or equal to 0, coming to the second case, and the third case is this, and the fourth case is this, are the 4 different cases of quadratic inequations which we identify in mathematics. So these are the 4 types of quadratic inequations which we are going to discuss in the session, and hence the roots of these quadratic inequations are called solution of the given quadratic inequations. Now, there are 2 methods of solving of quadratic inequations. One is the algebraic method and the other is graphical method. So initially, to start with algebraic method of solving of quadratic inequations. So let's take an example problem and see how we can solve the quadratic inequations using the algebraic method. So let's take the example problem: x squared minus 10x plus 21, which is less than 0. Now, I want to solve this quadratic inequation. Clearly, this is an inequality because this is less than case. Therefore, to solve this quadratic inequality using the algebraic method, I initially find the factors. So, when I factorize the left hand side of this inequation, I get this to be x minus 3 times of x minus 7, which is less than 0 on factorization using the factors process. Now, once I get the factors on the left hand side with inequality on the right with less than 0, let's see how we can use the algebraic method. Now, as I see here, since is less than 0, that implies I identify that x square minus 10x plus 21, the expression x square minus 10x plus 21 is negative, is how I identify the inequality. The whole inequality, the whole of the left hand side being an algebraic expression which is less than 0, implies the quadratic expression x square minus 10x plus 21 is negative value, being less than 0. Now, when this is negative, my coefficient of x square, which is generally denoted with a, here is 1, because 1 times of x square, which is 1, is also positive or greater than 0. Therefore, we have previously seen a theorem connecting the algebraic expression ax squared plus bx plus c and a. with their signs. So when the expression ax squared plus bx plus c and a are of same sign, then we know that the expression will have its values lying between. So let's recap with the theorem which we have discussed connecting the coefficient of x squared and the algebraic expression. So therefore, as I see from the expression and coefficient of x squared, they are of opposite signs, one being negative and one being positive. Therefore, this implies the expression x squared minus 10x plus 21 and coefficient of x squared, which is 1, are of opposite signs, Now when they are of opposite signs, we have the theorem which says that, therefore, by theorem, x lies between the two roots alpha and beta is what we have seen as the proof of the theorem in the previous sessions. For this being of opposite signs, x lies between the roots, and the roots here being 3 and 7 implies my alpha is 3 less than x less than 7 is what is the solution set for the given quadratic inequality. So therefore, as I see that for an expression x squared minus 10x plus 21 less than 0, my solution is all values lying between 3 and 7. That is, I write this in the form of solution set is given by x such that x belonging to real numbers such that 3 less than x less than 7 is what I get as a solution set for the given quadratic inequality. So if I see this on the number line, I clearly identify that if I have minus infinity on the left and plus infinity on the right, then 3 and 7 here, then the values of x which lie between are all the values in the region between 3 and 7, excluding this. So I get this to be the number line. So solution of x is between 3 and 7 but doesn't include 3 and 7, and hence with the open circle is what we understand the solution of the given quadratic inequality. Now let's do the same problem using the graphical method. Now that the algebraic method is one of the methods of solving the quadratic inequalities, of course using the previous session of the theorems. Now the second method through which I can solve the quadratic inequations is the graphical method. So as the name itself suggests, graphical method, this method includes the graph of the given quadratic equation or the quadratic function. So let's see how we can solve the problem using the graphical method. To take the same example problem, I have x squared minus 10x plus 21, which is less than 0, which I want to solve using the graphical method. So initially, I would like to sketch the function, the left-hand side function, which is y equals f of x, that is 10x squared minus 10x plus 21. So this is the quadratic function which I have extracted from the given quadratic inequality. Now I would like to sketch this function. This. Now that we need to sketch the function y equal to x squared minus 10x plus 21, to sketch the graph, there are three basic essentialities which we require. One is the x-intercept, the y-intercepts, and the table of values. As we have already discussed about sketching techniques, initially I would like to find the x-intercepts of the graph. Now we know that x-intercepts are obtained by taking y equal to 0 and y-intercepts are obtained by taking x equal to 0. So initially, to find x-intercepts, I take y equal to 0. Is equal to 0 is what I get, and then y being this equal to 0, when I factorize, we have already factorized in the previous session with this being x minus 7 times x minus 3 equals 0, and therefore I get my x-intercepts, which are 3 and 7, using the factors. This makes me understand that the graph cuts x-axis at 3 and 7 is how I understand x-intercepts connected with the graph. So now that the graph cuts or crosses x-axis at 3 and 7, let's see where the graph crosses y-axis equally, that is the y-intercepts. Now to find the y-intercepts, as in the case of this, I equally have my x equals to 0, and therefore when I substitute x equal to 0 in the given function, I get y-intercepts, that is y equals 0 square minus 10 times of 0 plus 21, which is 21. So this is the y-intercept, and these are the x-intercepts, that is the graph crosses y-axis at 21 and the graph crosses x-axis at 3 and 7. Similarly, I have to take the table of values, which I need to take in case of the first thing. Randomly take around 4 to 5, with one of them being x and y, and then with different values. One, 2, 3, 4, and 9. So randomly I take values which are away from the roots and in between and outside. So I've taken two values which are away from and one of the value, and then I took the other one through which I got between 1, 4 and away from 7, that is 9. So let's take some random values in the table of values, which I took few values before 3 and few values between 3 and 7 and few values away from 7. So using this, when I have x equal to 1, I have to see what is the value of y. So initially for x equal to 1, my y value is x squared minus 10x plus 21, which on substitution gives me 22 minus 10, which is 12, is what I get when x is 1, y is 12. Similarly, when x equals 2, let's see what is the value of y. So when I have this x equals 2, I have 2 squared minus 10 times of 2 plus 21, which is 21 plus 4, 25 minus 20, which is 5. Therefore, this is 5. When x is 3, we have already proved that y is 0 because it is the x-intercept. So I need not simplify for this. Similarly, when x is 4, my y is 4 squared minus 10 times of 4 plus 21, which gives me 16 minus 40 plus 21. This on simplification gives me 21, 31, 37 minus 40, which is minus 3. Similarly, when x is 9, I get my y as 12. Is how we get the table of values for the different x values as considered. Now we will plot the graph using these table values, x-intercepts and y-intercepts. So let's see how the graph of this can be sketched using the basic x, y-intercepts and the table of values. So let's take x and y coordinates on the real xy coordinate system with this. Being x-axis, y-axis, and then origin 3, 4, 5, 6, 8, and 9, which I took on x-axis, and of course -1, -2, etc. on the left. Then the y values being here 1, but because my y-intercept is 21, I would like to reduce the scale, increase the scale with 1 centimeter as 5 units. Therefore, I get this as 5, 10, 15, 20, 25, 30, etc. So this is what I get as the suitable scale for x and y axis. So in this case, initially I mark the x-intercepts and y-intercepts. My x-intercepts are 3 and 7, that is the graph crosses x-axis at these 2 points, and my y-intercept is 21, implies approximately slightly above 20, that is this. That means the graph crosses y-axis at this point, is how we understand. Now let's plot the other points from the table of values, where my first coordinate, each of the coordinates are given by 1, 12, 2, 5, 3, 0, 4, -3, and 9, 12 as taken from the table. So let's mark the first point, which is 1 and 12, which comes approximately here. Now similarly, I plot the second point, which is 2, 5, somewhere out here. And then finally I have 3, 0, which is already plotted on the x-axis, and 4, -3, which comes this here. And then I have 9, 12, which comes somewhere here. So I got the set of points which I'm going to join through the smooth continuous free hand. So therefore, as I proceed, I see that my points which I join here are just I get a sort of a shape which is like this, which I can clearly see passing through x-axis and passing through y-axis respectively. Now the equation of this parabola is y equals x square minus 10x plus 21, and this shape of the parabola will decide on what will be the solution of the inequality x square minus 10x plus 21 less than 0. Now as I see that clearly, how we connect this with the inequality is that the whole of the expression which is denoted by y or f of x is less than 0. That means we choose those values of x for which y is negative. Now as I see, my y is positive on the upside of the origin and y is negative down, x is positive and x is negative. Therefore, I search for those values where y is less than 0 or negative. So because this is the region where y is negative, therefore the graph along this region is what will decide the values of x. It is very important that the sign of y will decide on which region the graph requires the respective x values. So y negative in the down region, I see that this is the region where the graph is negative. So this is the region which is required out here where the whole of y is negative. That means for this is the region between x being 3 and 7 for which the y is negative. any value I take before 3, the y starts coming to the positive side. Any value of x I take on the right takes the y value to the positive side, but any value I take between 3 and 7 takes it down the x-axis, that is, it comes towards the negative side of y-axis. Therefore, for the inequality this being less than 0, my x value should be between 3 and 7. Therefore, I conclude saying that implies x lies between 3 and 7 is how clearly I see in the region. For the region between 3 and 7, the graph is downwards in the negative side of y-axis, but anything before 3 and after 7, it crosses to the positive side of y-axis. But I want the negative, therefore between 3 and 7 is the answer. Is how I understand this graphically.